Lecture 25. So last class we have seen how to represent the phase noise of a n-stage ring oscillator, right? So I didn't show you the complete derivation, but I have shown you all the major steps in getting to this derivation. If you take an inverter, how the NMOS and PMOS transistors noises are going to affect the output phase noise, I gave you an intuition on that. Now you can cascade a number of inverters, you will get a delay line. So that delay line will have some phase noise profile, right? A phase noise PSD. Now when you go from a delay line to an oscillator, now you know how to relate the PSDs. Right? Whatever was the phase noise profile of the delay line, that gets multiplied by 1 by f square. So the exact expression is f0 by pi f the whole square. But the key part to remember is that it is going to get multiplied with the 1 by f square factor. So if I were to look at any oscillator profile, right? So let's say this is at some f0. Ideally you expect to see an impulse. Now with phase noise present, you will see a skirt around it. How do you think, what do you expect to see in this skirt? What sort of profile? But now you know more information, right? It's going to get multiplied with 1 by f square. Now, typically you think about flicker noise and thermal noise. So, flicker noise will appear with what sort of profile? 1 by f, but if I'm looking at an oscillator, it becomes 1 by f cube, right? So you would see a 1 by f cube region, and then it will be followed by a 1 by f square region, right? So in close-in frequencies, that is, as you come closer to the f0, you expect to see a 1 by f cube profile, assuming that I've sketched it in log. And then far out frequencies, as you move away from f0, you expect to see a 1 by f square noise profile. So this is something that you can remember in general, right? Now, we said that to, so let me quickly write out these expressions because I'll have to refer to this during the lecture also. So what is the expression for S5 I of F? You can read it out from the board. So it's F0 by F the whole square. 1 by 2 ID square into SI NMOS. What is the value of this factor? 4 kT gamma GM. But this SI NMOS is for two-sided PSD. So it becomes 2 kT gamma GM, right? And I can replace this GM as 2ID by VGS minus VTH. What is the value of VGS? Just VDD, right? It was solved for VGS equal to VDD. VDS value was equal to VDD by 2. Okay. This plus SI PMOS plus 2 kT by ID into VDD. Now the second expression is for S5 flicker. So you see F0 square by F cube into 1 by 4 N ID square into S 1 by F NMOS plus S 1 by F PMOS. And then we replaced both flicker noise profiles with the expected expression. So then you got a GM square outside. And here you have Kn divided by and then you get twice of WLN into COX plus Kp by twice of WLN into COX. So you have these expressions for the This is 2. So you have these expressions for the phase noise component due to white noise as well as flicker noise. Right? So you don't have to by heart these equations. Feel free to write it on the piece of paper during your exams and bring it. Right? But it's more important to be able to analyze given this expression. Okay. Now we also said that the phase noise you can see at the output of the oscillator is related to how much power you burn in the oscillator. Therefore, to compare two oscillators, we have to define a new parameter called as figure of merit. What was the definition for figure of merit for an oscillator? So this is 1 by power is usually reported in milliwatts when you write this expression into the phase noise into F0 by F the whole square. So you report the phase noise at a particular offset frequency and the same offset frequency is to be used in the equation. So one question I had asked is, what would we like this FOM number to be? Is it better to make it larger or smaller? Larger, right? Because that would mean that the phase noise is less, power is also less. So if you are comparing two oscillators, the one with larger FOM is the better oscillator. Okay. Now the second question is, does the value of FOM change depending on the offset frequency I consider?
Depends on the noise which is dominating it, the white noise should not be.
So the white noise profile appearing at the output of the oscillator is not really white. Comes out as 1 by F square.
If this term is S square, white is the dominating noise. That goes down so that
that is true. Then it won't make a difference.
But if that goes, if it's a flicker noise, then F square and F cube will be there. So when F cube is there, the numerator is there.
Correct. So what it means is, if you really want to compare two oscillators, one, you should be comparing them at the same offset frequency. Two, it also makes sense to report the FOM during this regime of 1 by F cube as well as in the 1 by F square regime. Right? So you report, find out an offset frequency where both the oscillators are in the flicker noise related 1 by F cube region, report the FOM there. You also report an FOM for a far out frequency where both of them are in the 1 by F square regime. Right? So have both FOMs calculated when you are comparing the two oscillators. Okay. So now we get back to our attempt at designing a very good ring oscillator with as many less steps as possible. Right? So we designed a ring with 3 stages. We started out with a reference design with minimal sizes and minimal number of stages, and we found out that it had a very large oscillation frequency. Then we are now doing certain steps to bring down the oscillation frequency. Right? What all did we plan to do? You could add additional capacitance at this node. Right? The second method was to increase the number of stages. What was the third method? Increase the length of the transistors. And finally, you can add a divider at the output. We compared all 4 methods in terms of power. Can you look back and tell me how the results were? If I assume that the reference design had a power P0, what were the powers for all these stages? Look at your notes, feel free to discuss. It was same. When you increase the number of stages?
Same.
It was same. When you increase the length?
Root M.
This became root M. And in the last case? So this is P0 plus some P divider. Right? And now we have started comparing them based on the FOM. Right? What did we find when you increase CL? What happens? You are adding additional capacitance. So you have both the expressions here. How does both of them change? Does the S5 white change if you add additional capacitance? No. What about S5 flicker? Both of them do not change, right? Power is also not changing. Therefore, FOM remains the same. Now we'll compare for the second case of increasing N. Right? We know that the power remains the same. So now I can compare S5 white normalized to F0 by F square. The reason I'm already normalizing it is because the FOM has that expression. Right? And you can also look how S5 flicker normalized to F0 by F the whole square is varying. Right? Once you know these two, then you will be able to comment about the FOM. For what part? So now that you have two profiles for the phase noise, you can tell me whether the FOM is increasing for close-in frequencies or far-out frequencies. Okay, so you're talking about S5 flicker, right? Now when you increase N, you have N in the denominator.
That's flicker, yeah, right?
So we are talking about the close-in frequency, right? During the flicker noise regime. Are you able to follow? Right? Please ask if you have any questions. So you have N in the denominator, you increase N, you expect S5 flicker to reduce, right? Which means this factor is now reducing. Therefore, your FOM will improve, right? So this improves for small f. What about S5 white of f by F0 by f the whole square? It doesn't depend on n. So it remains the same. So this factor is reducing, this remains the same, right? So FOM for far out frequencies remains the same because the power is not changing, the phase noise is not changing. This is clear? Then, which one? This is not FOM, right? The FOM expression has power into phase noise. So, this term S5 flicker by F0 by F square is basically this phase noise by that factor. So, you have to multiply this power with the term written here. So we now come to that very interesting case where we got an improvement in the power. So we are increasing the length. So to reduce your frequency from F0 to F0 by M, by how much did you have to increase your length? You have to increase this by root M times. Okay. Now given this information, so we know that the power is becoming P0 by root M. Right? What about the other two factors?
We become 1 by M.
White noises?
We become 1 by M. Okay.
White noise, so you don't have to worry about the F0 by F the whole square term, right? So you have to look at the rest. What happens to ID? ID decreases by, so you have a 1 by root M factor in the denominator. So it is increasing. Why does it make M?
ID square.
Right, but you also have GM in SINMOS. So you can cancel out this ID and this square.
Okay.
Right, so you have 1 by ID. This ID will now become ID by square root of M. So that square root of M comes in the numerator. Right? So this one will increase by root m. What about S5 flicker? Why does it increase by root m?
So that GM and ID will cancel.
So GM and ID square will cancel, right? It decreases by root m. Is that clear to everyone? Because you have the length here, right? This is that process dependent coefficient in the flicker noise. The flicker noise expression is k by WLCOX into 1 by f. So this is the... Yeah. So this is now decreasing by root m. So can you quickly tell me what happens to FOM here and what happens to FOM here?
Same.
So you have all the expressions here, you can look and tell me. FOM remains the same?
Yes. That is by M.
Right? This increases by? So how do you think this method compares to the previous method?
That was reversed. So remaining same for the larger and increasing for the smaller. Here it is reversed.
Is it? S5 white, is it for close-in frequency or far-out frequency?
Oh, okay. Sorry. Order I.
Right? And so for close-in frequency, how do you think these two compare? By how much does the FOM improve here? M times. Because you have n directly in the denominator here, right? So here also, so it looks like these two methods are comparable at this stage, right? Yeah. Now the last scenario is wherein you add a divider. So before you comment about the FOM directly, first tell me what is the transfer function, right? So if I have a divider, I know that if the input frequency was some F0, the output frequency is F0 by M, right? It's just a frequency divider. How do you think the phase is going to behave? Because we are now looking at the phase noise PSD. If I can find out the transfer function for phase, calculation of the PSD is very easy, right? So if the phase here was phi naught, what do you think is appearing at the output? Y integral? So I'll tell you a quick example to try this out, right? Let's say I take a square wave. Let's say this had frequency F0. I pass it through divide by 2. My F out is going to look like this. Right? Let's say this edge had some phase noise. Going to simply call it as some phi n here. Right? You know how to convert this phi n to some Tn. Right? What do you think will appear here? Is the Tn going to appear here as it is, or is it going to get corrected? You can think of a divide by 2 circuit constructed using a flop. Assume that the flop is adding no errors at all.
It will get the same. That should be the same.
So, okay, then yeah. Time period is changing, that I agree. Right? This is going to be 2 times T0, where T0 was 1 period here. My question is, if this edge had a shift by Tn, this also will shift by Tn. Right? If the divider is not adding any noise, this has shifted by Tn. Can you quickly calculate what is the output phase noise at this edge? Is it same as phi n, or is it something else? It is half? 2 times? So I got 2 answers. 2 times half? Only possible solution is it remains the same. So is anyone suggesting that? Why half? Because time period has doubled, right? So this is going to be phi n by 2, right? So if you had f naught becoming f naught by m because of a frequency divider, your phase is also becoming this divided by m, right? So if you were looking at a voltage signal a naught cos of omega naught t plus phi n, the output will be a naught cos of this whole thing by 2 plus phi n by 2. The total phase is getting divided. Is that okay? Right. So which means if my ring oscillator, this had some profile, let's say S phi oscillator of f. So now I'm not differentiating between flicker or white or anything. The total profile I'm considering. This is going through a transfer function given by 1 by m. What would be the PSD at the output? So this is S phi oscillator or of f divided by m square. Okay. Now let us go back and look at the FOM expression. Right. For now, we will assume that the divider is ideal. It is not adding any phase noise of its own. It is not consuming any power. Right. We'll assume a very ideal divider. I just want to see what happens to the FOM with these assumptions, right? Then we can extrapolate from there, which means the FOM at the output of the divider is what we are trying to calculate. Power remains the same. We are calculating only the oscillator power. It should be the whole power. So what I am telling you now is, I am assuming that the divider is ideal, right? This takes no power. It is adding no phase noise, right? And let's say this is assuming some has some power P naught and has this phase noise profile. That assumption is very off. Yeah, that assumption is very off. I agree, right?
Assuming no phase noise, that is still reasonable.
Yeah, so I understand that this assumption is a little hard to think of. But let's start from here, then we will add the power of the divider afterwards, right? The assumption, what we are trying to do is, if the divider is as ideal as we can get, do we see any improvement in the FOM? Right? So that is like the best possible FOM you can get at the output here. So that is what we are trying to calculate. So the expression for the FOM is 1 by power into phase noise into f naught by f the whole square, right? So power remains the same because we are considering only the oscillator power. Phase noise has become whatever was the earlier phase noise divided by m square, right? The frequency has also come down by m, right? So you have a 1 by m square factor here, right? So there is no benefit in terms of FOM, right? So under these conditions, FOM remains the same. So now when you add the divider power and its phase noise, the FOM is going to degrade, right? Which means this solution is not better than the other solutions. That's all we wanted to show, right? So FOM will degrade if the divider power and Pn are considered. So now let me go back to the table we started constructing here, right? So in the first case, FOM remains the same. If you increase by n, what happens? Close in or far out frequency? Yeah. So FOM improves for close in frequencies. What about increasing L? Same, right? So FOM improves for close in frequency and this one degrades. So now that you have seen 4 methods and how the power and FOM are changing, which of these methods do you think you will rely on? So either increasing the length, if power is more important, you will increase the length, or you increase the number of stages. Is there a reason to choose increasing number of stages over length? Why? What comment can you make about the rise time and fall time of the signals? If you are increasing the length, right, to get a lower frequency but with 3 stages, right, then at each stage the signals are taking a lot more time to rise and fall, right? So it's going to be very distorted waveform, right, which means you are probably going to burn a little power in the buffer following that, right? Now if you increase the n, you'll have better rise and fall times. So something to consider. These are trade-offs that you will know once you start implementing, and then you will make a decision. It is going to look more like a sine wave. Current is reducing. Yeah. So current is reducing, which means to charge the same capacitance, you will take a longer time. Right. So now again, this comparison. So this is what we have gotten from the theory while making a lot of assumptions. So you can expect to see some changes as you run the simulations. But this is your underlying theory. Then you will run the simulation and then you can choose what is better. So in this particular case, you might directly choose increasing N or L. And if you want, you can do a comparison between the two. Right? So let me show you the results for all 4 cases. So this table was taken from the textbook by Rasavi on PLL, right? So again, they designed a minimum sized ring VCO with 4 stages in a 40 nanometer process. Ran the first simulation and found that it had a frequency closer to 22.6 gigahertz, right? And then they adopted the 4 methods that we discussed to bring down the frequency. Right? As you can see, the frequencies have not come to the exact 2 gigahertz they want. It's in the range. Right? Once you are in the range, it becomes much more easier to bring it to the exact value. Okay. So power is reported. Like we expected, power is smallest for the case of increasing the length of the transistors. Right? The supply sensitivity is now reported directly, kVDD. Right? All of these are, except the greater number of stages, the rest are for n equal to 3. Right? So looking at it, you might think that this has a very good supply sensitivity, but then you also see that it is running at a slightly lower frequency. Right? We should be looking at kVDD by F0. Right? Once you normalize it, you'll find that they are roughly in similar ranges. Even now, they are actually in a very close range. It's not like there is an order of magnitude different. Right? So in the initial design, when it was at 22.6 gigahertz, the kVDD was closer to 50. When the frequency came down by 10, the kVDD value also came down by 10, which is why we should be looking at kVDD by F0. Right? Now the phase noise is given at 1 megahertz offset and at 100 megahertz offset. At 1 megahertz offset, this is in the 1 by f cube regime, and this is at 1 by f square regime. Right? And you can see that the FOM is also calculated. So as expected, you see that the far out frequency FOM is similar for all 4 cases, but for close-in frequencies, you see improvement in these 2 cases. You expected to see similar improvements, but the long channel transistor is giving you slightly better improvement because of certain second order effects we did not consider. So the values of Kn and Kp, they are also functions of length. So these things becomes a little tricky to account for when you're doing the theory. So that you will find out from simulation. Right? So any questions on how we went about designing a ring oscillator?
Design 2, the power is more than design 4.
Power is more than design 4. This they have not considered dividers, power consumption, and phase noise. Right. So this is basically your power of your starting divider. And sorry, this is basically the power at which you started. Now on top of it, you see that the frequency is also higher.
I guess they should have considered, because then if they have not considered it.
They have not considered it.
Then why is that not equal to that of the design one?
Which one?
Should equal to the design 1 and design 4. Or it should remain P naught, right?
Why should it remain? So theoretically I understand. But now you have increased the capacitance, right? All our power calculations have been considering only the power required for charging the capacitance. Now in the presence of the capacitance, your rise time and fall time are going to degrade, right? Because of which the short circuit power consumption is going to increase. But looks like the short circuit power consumption has reduced here, right? Yeah, so second order effects is all that I can tell you now, but I'll also have to think why it has reduced. This, let me also think, and then I can give you an answer. But it's not necessary that they need to have the same power, that I can tell you straight. Okay, so one thing we all understand by now is that if you try to simulate, let's say you got it perfectly to 2 gigahertz, then you try to simulate it across corners, right, across PVT corners, you know that the frequency is going to change. So if you were interested in roughly being around 2 gigahertz, you can follow this method. Around PVT, you will have a small variation in the frequency. Maybe in that application, you are okay with that variation. If you are not okay with that variation, what can you do? You have to give a feedback, right? So the first step in getting to that would be to make sure that your oscillator has tunability in the frequency, right? So now comes the idea of voltage controlled oscillator. So you can basically take this ring and make it tunable, right? You want to make its frequency tunable. So instead of a single inverter, what will you do? If one inverter stage was like this, what all can you do? This is something you know, right?
Change the TD.
Right, you have to change the TD, which means you can either have a tuning capacitance or you can tune the current, or you can use combination of both. You can, right? You can take the same unit and then take odd number of such inverters, put it in feedback and get it, right? Which means the starting point of design for your circuit is slightly different. So you'll have to figure out the methodology to get to the final stage, right? So, but similar principles would still apply, right? You figure out what all are the things that you can possibly do, and then quickly figure out which of those are going to give you benefit compared to the others, and then simulate only for those. So when you tune this, you are now expecting to see some F versus VC curve, and depending on how you have designed, you may get a positive KVCO, right? The slope of this becomes the KVCO, or you may get a negative KVCO. Okay. Now, so this sort of tuning is called as continuous tuning, right? Because all possible delay values are possible. On top of this continuous tuning, you can have discrete tuning to improve the range. Okay, let me explain what I mean by that. So this is F versus VC. Now let's say across all corners, you have ensured that when you change your VC value, you get so much range, right? If you wanted higher range, you put in one more control, right? We'll discuss about what that control can be, and have one more curve like this. Is that okay? So one thing that you can possibly do is I'll show tuning only on the charging current. Right? So if you have some, let's say, VC bar connected included here, it's going to give you some tuning. Right? Along with this, let's say I add one more transistor. This is controlled by a digital bit. Okay, so this is either 0 or 1, meaning it's either VDD or ground. So now if this is 0, which means you have more current flowing through this. The current available for charging is higher. It is constant. So that is constant, plus through VC you have a tuning. Right? So this way you can get bands of tuning ranges like this. Right? So typically we call this as frequency band. You switch from one band to the next.
This way the digital is low, so you get the upper.
So in this particular example, it has been designed like that, or is it? So if the digital bit is low, you have less delay. Digital bit is low, less delay, so upper current. Correct. Okay. So now it is also possible that you have continuous tuning in current, but you have discrete tuning in capacitance. So you can have, let's say, 2-3 capacitances connected like this. Okay, let me call this as C1 and C2. So now you can do continuous tuning through the current, and then to switch the bands, you can set these switch values. Right? You turn on the switches so that the capacitance seen is different. Now, if I was planning to put 2 capacitances, any suggestion on how I should choose the value? Let's say I chose my C1 as C0. Right, some value C. Right? Any suggestion on what my C2 should be? 2C. Right? Is that obvious to everyone?
You can get 3 different values. C, 2C and 3.
You can get 4 different values. 0, C, 2C, 3C. Right? So you choose it such that they are binary weighted. Is that clear? So if I chose both of them as C, right, you can get either 0, C or 2C. Right? But if you choose, so I can have 3 capacitances, then I'll choose them as C, 2C, 4C. Right? So you can get all possible, you'll get 8 cases. So even if you're choosing the currents here, constant current values, you make them binary weighted. Is that okay?
If you choose any 2 different values, you get 4.
If you choose any 4?
No, like any 2 different values, you get 4 different.
Right, but would it be uniform? That is possible, right? So if you have a very specific reason to choose it, for example, you know that some distortion is going to happen from the capacitor bank code to the frequency, then you can pre-distort the capacitance values, right? So, but otherwise the general method is to binary weight them so that they are equidistant. It increases by step size.
This circuit will deploy after we got the larger units like 22.6 to smaller like 1.9.
So your question is, if I were designing a VCO, do I start with a ring oscillator and then move to a VCO architecture, or?
Smaller then we will this.
Right. So if your aim was to design a VCO in the first place, you would start with a VCO architecture, not with a ring oscillator architecture without tuning ability. Right? So you would, but similar assumptions you would do. Right? You will say that right now there is no reason to choose a larger size, so I start with the minimum size. Then I do my first simulation, I find out what the frequency is and what is the range of the frequency. So now how do I bring it down? What all can I do to bring it down? And that is how you would proceed. So the thought process remain roughly similar. The exact steps you choose will be different. Is that clear? Okay. So you can get discrete tuning by either using a capacitor bank or a current bank, both of them binary weighted. Now let's say we look at LC oscillator, right? How do you think we'll get tuning in an LC oscillator? Right? So you can either tune the capacitance, right? Which means with the fixed capacitance, you will add a tunable capacitance in parallel, right? Or it is also possible to tune the inductor, It gets a little tricky because anytime you add a switch in series with the inductor, its quality factor is going to degrade. Similar effect happens for capacitance also, but it's much more prominent for the inductor. And have you seen an inductor layout? You have seen chip layouts, right? If there is an inductor, you'll be able to make it out because it's going to take up a lot of area, right? If there is a transistor, you will not be able to make out an individual transistor from a distance if I were to show you a pic, right? But inductors are huge. So putting more inductors mean you're losing out on more area, right? It's metal line, right? And they will, you will have a architecture like this. Yeah. So instead of exactly circular, you will have lines like this. So this is one inductor, right? And then you can have coils if required inside. Then you can have differential implementation, etc. So even if you are tuning with inductors, you will typically have two inductors on chip. And the very interesting idea is, let's say this was L1 and this was L2, you'll have mutual coupling between them, right? And the value of this, how this M appears once you look from this direction or this direction, depends on the direction of the current. So you can switch the direction of the current and make this M appear as minus M. Right? So this is one way how tuning an inductors is achieved. So we'll not be able to cover it in this course, but if you are interested, you can look up more about it.
This will just change. The two discrete values are
You get only two discrete values, right? So what typically happens is you will have both inductive tuning and capacitive tuning, right? A small varactor tuning to get some range. On top of it, a capacitor tuning to get multiple curves like this. On top of it, an inductive tuning to get these four curves at a different value, right? So with all of this, you are able to now get a larger range. Right?
How do you decide which curve we have to buy?
How do you decide?
There are 8 curves, right?
So now that is a separate algorithm that you have to work out. Typically, so because we have not seen how the oscillator is in feedback, right? We will discuss this after we have seen how to put an oscillator in feedback. But that usually requires two types of algorithms. One to identify which curve and then how to move along that curve. Right? So two separate algorithms. Finding the curve also takes some. But the good part about it is finding this curve requires digital tuning. Right? Because you don't even need an ADC. Sort of like a binary search, right? So you will need some mechanism to detect the oscillator's frequency in a coarse manner, right? And then based on whether it is larger or smaller, you need to keep changing the code. So in 619, some of you have implemented a frequency lock loop, right? Where you detected the frequency just by monitoring the clock for a long period. Same algorithm you can use. Right? So you simply have to detect whether the frequency is within a range or greater than that range or smaller than that range. Then you change your code. So change it by one step, check again, change it by one more step. That's it. You always need a reference, right? Anytime you have a feedback, you need some reference to compare. So one more point about having these multiple bands is, you will have to make sure that there is no, dead zone between the bands. So, for example, let's say this band covered from here to here. If the second curve was beginning, let's say from here, you have a region here which is not covered by either of the curves. This should not happen, right? So what you will need to do is you will have to ensure that there is some overlap between both the curves. So now this region can be covered either by this curve for large values of VC or by this curve for small values of VC. Right? So you have some redundancy built in. Okay, alright. So now we have figured out how to tune the VCO. Right? We know how to design an oscillator. we have some idea about how to tune it. So we have a range of frequencies that we can achieve using this tunability. Let's now put this in feedback, right? But before that, can you tell me the motivations for putting this in feedback? List out all your motivations for putting it in feedback. So PVT control. So one is PVT control. What was the second answer? Why stability? Stability of what? So now we are talking about the error in the frequency, right? Error in the frequency across PVT. Yes. So then PVT control, right? What else? I mean, throw out ideas. If it's wrong, it's wrong. That's all.
Different values of different frequencies.
To get different values of frequencies, right? So, what are you basing that answer on?
You can given the frequency. Like if we didn't have feedback, once you fabricated the circuit, you could only get one frequency out of it.
Correct.
Now, since we have some feedback mechanisms, we can change the reference to change the frequency.
So the main statement you made is correct. I think this part is not matching up to that, right? Because so you're talking about some reference frequency, right? So is our aim to make sure reference frequency somehow controls the VCO, such that the VCO frequency is same as the reference frequency? Not necessarily, is it? Then what happens? So you can adjust, sorry, you were saying? Harmonics of FREF. Okay, so basically multiplying FREF by some integer, right? We didn't form the structure. FREF is the reference input frequency. We don't put a right, but we are going to put this oscillator in a feedback, right? So when we put the delay line in a feedback, we needed a reference clock. Similarly, here also we will need a reference clock. We are going to log the VCO frequency to something. So that something is needed.
This is going to be VREF, right? Should not FREF.
So this is going to be some, let's say, V0 into cos of omega Ft. Right? So it's some voltage domain signal, either a sine wave or a square wave with frequency FREF. So we haven't figured out what this feedback mechanism is, right? But the idea is that you can get multiples of FREF at the output, right? You can also have fractional multiples, right? So it's not, here it is not called as harmonic clocking, so we'll come to that in a minute, right? So, and one reason why we will want to do this, so you should all be asking me the question, if an FREF is already possible, right, a clean clock is possible, why not use that clock? So the clean clocks that we typically get are from crystal oscillators, especially the quartz crystal oscillators. Now they generate electrical periodic signals based on some mechanical vibrations inside, right? And it is, one, it is slightly costly. Two, it is not available for all frequencies, right? And it's typically available for lower frequency ranges. It's not available for very high frequency ranges, part one. And even if some of them are available for higher frequency ranges, they are more costlier, right? But you wouldn't be able to pick out crystal oscillators at 5 gigahertz and then, have tunability over it. So if you wanted multiple frequencies, you will have to use multiple quartz crystal.
Can those crystals drive large loads?
So you can bring that crystal signal on chip and then put as many buffers as you want. Right? Yeah. So these crystals are also bulky off-chip components. they cannot be integrated onto our regular bulk CMOS process. So one, they are bulky off-chip components. So if you want to put 5 different frequencies and you choose to have 5 quartz crystal, then your chip might be small, but the board on which you have placed your chip will be large, right? Which means the size of your phone is not going down, right? Because the PCB inside is larger. So because of these reasons, we typically have one crystal source for a chip, right? So you take one crystal, right? You take its output to the chip, and then you use it in multiple places to generate higher frequencies. So you can divide it down to get lower frequencies, multiply it to get higher frequencies, etc. So you can have as many of these components as you need, but have only one crystal oscillator. So this is what is typically for. So another reason is to get frequency multiplication. What else? What comment can you make about the phase noise or jitter in an oscillator? It is unbounded, right? So now if you put it in feedback, and if the reference frequency given as input is very clean, you are basically correcting your VCO clock with respect to this reference using the feedback. So this way you can also put a upper bound on the jitter that you will see. Right? Or in other words, you are going to filter the phase noise of the VCO. So far, okay? So now let us get to building this system. So we have a VCO, right? Let me call this output as M out. It has frequency F out. What all components do you think should be there? So we have a reference signal with, let's say, frequency FF. You have seen one time domain loop. So help me build this. You can use generic terms. What should be the first part here? It's a feedback loop. What do you have to do at first? You have to detect some error, right? Which means you need to compare both of them. Okay? So you will take your output and you will compare them. Right? What do you think should be the value here? It's a voltage, right? It's VC. So you are comparing something here. Then you may need to do some processing, probably filtering. And then you will get a voltage here. And that is going to drive your VCO, right? A very simplistic loop we have constructed. So now, one question I have to ask you is, what is it that we are comparing here? So one option is frequency. What else? Phase. You could compare phase. Anything else? So time and phase are similar. Anything else? So now we have to decide between frequency and phase. What parameter should we compare such that my VCO can be a stable oscillator? So let me, why phase? Why not frequency? Oh, we can figure out, right? If that is the...
Frequency is one thing is like it's a very large number, so like 600 megahertz and 600 megahertz.
So the difference is 1 megahertz.
How much is going to make the difference to be very small? So accuracy has to be very good.
So you said we already know phase detectors but don't know how to. But if you remember, PFD is called as phase frequency detector. We only looked at the phase detection part of it.
It has to match two frequencies to compare those frequencies.
So, right? So he makes a very reasonable argument that objective is to match frequencies, so why not compare frequencies? So let's discuss that with 3 scenarios. So let's say in the first case, I am comparing, I'm using a phase detector and I compare the phases. Right? So this, let's say, goes through some filter and I have the VCO. Right? So if I'm calling this as phi ref, I'll call this as the feedback signal phi FB. Right? Now if this loop is working correctly, we expect phi ref minus phi FB to be equal to 0. That is, the error is 0. Right? Let me consider a loop where you are detecting the phase error. So I have some frequency detector. We'll follow it up with some filter followed by a VCO. So here I am comparing Fref with F feedback. So Fref minus F feedback is equal to 0. Let me also show you a regular analog amplifier in feedback. So if this was some Vref and this is, let's say, V feedback, the feedback in signal, then we expect to see Vref minus V feedback equal to 0. So far okay? Now in the presence of non-idealities in this op-amp, what do you expect this value to be? Some offset, right? So if you lock frequency, in the presence of non-idealities, it's going to lock with an offset. If you lock the phase in the presence of non-idealities, this is going to lock with an offset, right? So if you are locking phase, can you also tell me the frequency relationship? How do you go from phase to frequency? Differentiate, right? You take the derivative of the phase variable. Phase to the frequency variation in. So then you will have omega ref minus omega feedback equal to derivative of this. Derivative of a constant goes to 0. So you see, if you are locking the frequency, it's possible that in the presence of non-idealities, you will have a frequency offset. And this frequency offset is very problematic. For example, let's say you were designing a clock for a processor. You told the engineer that it is going to lock to some frequency. He did a ST analysis based on that, right? But then because you have locked with respect to the frequency, in practice you can have an offset. This offset will be constant for a given PVT condition. But if your process corner changes or temperature changes by a large amount, this offset will also vary. Which means you cannot exactly predict this value, you can predict the range of values. Right? So it's possible that the STA analysis done earlier can fail because it was done for a particular time period. Now your time period has changed. Everybody understands STA? Timing analysis taking for setup and hold. Yeah. Right? Now, if you are thinking about a receiver architecture, you use a carrier frequency to demodulate the signal. Right? And that carrier, the LO frequency has to be same as the carrier frequency in the incoming signal. Let's say your LO had a frequency offset. Then you are demodulating some noise instead of the information. You are entering into somebody else's channel. Right? So that is a problem. Another nice way to understand this is, how can this offset be constant? It is constant for a given PVT. Right. Yeah. So so if you were, when you were designing your DLL, you had a static phase offset, right? And that static phase offset for a given process voltage and temperature, it was constant. Okay? Same thing.
It was changing for cost.
Correct. But not, if you are running one long simulation, for that given condition, it was not changing from cycle to cycle. If it was changing, then we wouldn't. It wasn't changing, right? If it was changing, then it's either jitter. Now it could be a deterministic jitter if it's because the DLL is going back and forth from the, right? But then it is called as jitter. On VC? But your offset was constant.
That is a ripple.
Yeah, so the ripple on the capacitor voltage. Now the VCDL delay, you are measuring it at a particular time instant on that ripple waveform. Right, so in every period, you are sampling it at roughly the same position, which is why the offset was remaining constant. Is that clear? You can ask me at the end of this. Okay. So the other example I wanted to give you is, let's say some data was coming in, right? And the data is coming in at some frequency, let's say F data. Now, if you wanted to sample this data using a clock, ideally your clock should have the same frequency. Correct? If your clock had an offset, as you keep moving into future timelines, you are going to be completely misaligned with respect to the data. If you are sampling the data with the rising edges. So due to all of these reasons, frequency offset is something that we cannot live with. Right? A constant phase offset, on the other hand, is okay. It's not very ideal, but you can manage. Right? So therefore, even though what we wanted is a stable frequency, instead of locking for frequency, we will lock for the phase. So what should we call this loop? It's locking the phase. Phase locking. So this is a PLL. So we are going to deal with a phase locked loop, or in short, called as a PLL. Right? Now, I can, so in the present structure, it's not very obvious how I can get a multiplication out of this, right? So if you wanted to get, let's say I wanted my V out to be some beta times Vref, what do? You connect the resistor. How do you connect it such that you get what value in this feedback? You should have 1 by beta here. Right? Is that clear? You would connect the resistor here. So you would basically have 2 resistors connected here, such that the output here is V out by beta. Right? And then you are comparing Vref to V out by beta. Right? So what should we do here? So something to be done in the feedback loop. Right? So I add a divider. So I can add a divider, let's say, which divides by M. Then my phase as well as frequency get multiplied by M. Okay. So my F out will be equal to M times Fref.
What is M?
M is the division factor.
Objective was to get equal.
Need not be equal. You can either, if you wanted equal, you will choose M as 1. You will not connect anything in that path. But if you wanted twice the frequency, so let us take that example, right? So let's say I have Fref to be some frequency like this. Right? Now I wanted my F out to be equal to 2 times Fref. Okay. So I'm going to sketch 2 more waveforms. One is the frequency, one is the voltage waveform here. So we'll call this as V out. And one is the voltage waveform here. We'll call this as V feedback. Okay. How do you expect, so this was my Vref. How do you expect V feedback to look like under steady state conditions? It has to match, right? So your V feedback will also look exactly like this. Right? Then how will V out look like? So V out is the signal here. It has been passed through, let's say, a 1 by 2 divider. Right? So if V feedback is given to you and you know that this is divide by 2 of some signal, how would the signal look like? It has to have twice the frequency. So the signal is going to look like this. So in a PLL, you will always have, you are comparing F out to be same as whatever is the frequency of the feedback signal. Now, if this feedback signal is F out, sorry, yeah, I should write it the other way. So your Fref will be same as the feedback signal. Now, if this feedback signal is some F out by M, that means that F out is M times Fref.
If I want M to be fraction, how will I divide it?
So there are dividers that are called as integer dividers and fractional dividers, right? But what fractional divider does is it achieves the fraction on an average. So if you wanted divide by 2.5, in one cycle it will divide by 2, the next cycle it will divide by 3, and then it will keep repeating this. So the output you get is not completely divided by 2.5, right? Which means it will have more spurs if you look at the spectrum. But if you use it in a feedback loop like this, you'll have a transfer function from here to here. And you rely on that transfer function to suppress the unwanted spurs. Okay, so here the signal you get here, right? It will have some strength at the required frequency, right? Which is going to be Fref by M, where M is an integer. You will also have additional spurs in these points, right? But then this whole system will have a transfer function going from this point to this point, right? And that transfer function will turn out to be from here to here, it is low pass. So you rely on that to suppress the unnecessary spurs. So you can have some particular frequency here, right? Some profile here. You can have some profile here. What finally matters is what VC is seen by the VCO, because the VCO is the one that is giving you the frequency. So it's possible to design, so a lot of design considerations go into how you design the divider, how you will switch between the integer values of division, etc. But it is possible to get a fractional multiplication at the output. Yeah. Correct. Correct. So much like in DLL, we will now build the DLL loop and analyze its small signal model and check whether it is stable. So that is your question, right? Yeah. So we will do that. So before we end the class, how do you think we should now start? We have a rough idea about how to connect the loop, right? Is there a loop that we can think of as a starting point and make some modification there to get to the PLL? DLL, right? So why don't you start with a DLL? See how you can take a DLL to a PLL. So give it a go. So for now, assume that the division factor is 1, right? You start with basics.
Just remove that wire where TREF is getting connected to the VCDL.
TREF is... So you are thinking of replacing the VCDL with the VCO.
VCO? Straight wire was there, that connects TREF. Then remove that one.
So construct it. Please give it a try. By then I'll figure out what's wrong with my... So this was the PLL loop that we were working with. You have a PFD that is comparing the reference and the feedback signal. PFD gives you up, down, controls the up and down currents, and you develop a voltage VC across this capacitance. Right? So now I want to make this into a PLL. What is your suggestion? Remove this part and replace this with a VCO.
Yes.
Right? Okay. So let me do that. So instead of this, I now have a VCO. So far looks okay. Now can you sketch the small signal model for this?
We just forgot the and divided.
So let's assume that the feedback is unity, right? Right. Otherwise, you can simply have a divide by m in this stage. Right? Okay. So that's a very nice question. I'll come to that after you have sketched the small signal model for this. Yes.
If I want that my m should be 1, 2, 3, 4, 5. I want my this one requirement. So in my VC here the graph f0 versus VC. All this m1, m2, m3 all should be there in my.
All should be there. Yeah. Otherwise it cannot log.
And in this configuration it is assuming 1 is fine, not that 8 lines.
You are assuming? We'll assume the ideal VCO characteristics. Let's not complicate it because we are still trying to understand the loop, right? So you can assume that the with respect to VC, you have omega out in this shape. So omega out is some omega naught plus k VCO times VC. What is the small signal model for this? How would you represent the output of the VCO? What is the transfer function in a phase domain model? You know this. So that is from here, right? So this becomes ICP by 2 pi into 1 by SC. What will you replace VCO with? Integral. So in S domain, 1 by S, right? So you will have KVCO by S here. So did you construct the small signal model?
I forgot how 1 by S.
So this is omega out. To get phase, you will have to integrate. Integration becomes 1 by S. So let me construct a small signal phase domain model quickly. Right. So you'll have phi ref, this is phi feedback. What do these two components give you? You get ICP by 2 pi into 1 by SC1. SC, right? This into KVCO by S, and this gives you your output. So because I don't have any divider in the feedback path, this is same as your phi feedback. So for tomorrow, please analyze if this loop is stable. So you have to sketch the magnitude and phase of the loop transfer function. So derive L of S, right? Then you sketch magnitude of L of j omega and angle of L of j omega, and then calculate phase margin. This is angle is minus 180. Why?
Yeah, square.
So you have two poles in the origin. So is it stable?
Just stable.
Why is it just stable?
Then stable. If something happens, I can try.
How is it stable? Both of them are at origin. So what is the phase margin?
0.
Phase margin is 0.
It's
on the j omega axis, right? Basically in the closed loop. Closed loop poles will be on the j omega axis. It's positive feedback.
No, I don't understand.
So you have 180-degree phase shift. Right? So you have 180-degree phase shift and you can check what is the magnitude of L of j omega at that point. Right? So if you have 180-degree phase shift from here and you have a minus sign from here, overall the loop is positive. Right? So this is an oscillatory system now. How do you think the output is going to look like? So I have left you with a lot of questions. We'll answer them one by one. Okay? Yeah. Thank you.